Good morning. Welcome to another session on environmental impact assessment.
Unit 5 Case Studies. Course outcome describe the EA for various infrastructure projects. Learning outcomes explain the EA for water supply schemes. Physics outcomes explain the impacts of water supply scheme on the environment. Right, so we already seen the scope and we have seen part of the environmental impacts. Right, we will start from wherever we left in the last half. Groundwater, right, so called quantitative overuse of water sources. Groundwater is the most sensitive resource, and as such, the determining factor that governs its regenerative capacity is the recharge rate, which often works out only a fraction of the mean annual precipitation. The significance of the recharge rate can be seen from the following example, where groundwater is recharged at 80 millimeters, right, per annum from precipitation. An average village well system composed of individual wells with a system output of around 8,000 meter cube, right, requires a watershed of about 10 hectares or 0.1 kilometer square. However, when the recharge rate is only 1/10 of that quoted above, that is where it is only 8 millimeters per annum, the watershed needed by the well system goes up to 10 times 100 acres or to 1 kilometer square. Right, so when the recharge rate is high, right, you need a small watershed meaning you need a small area for collecting the water. But when the recharge rate is very low, you need a large huge area to replenish the groundwater system. This example demonstrates the extreme sensitivity of the water balance in cases where groundwater recharge rates are lower than 10 millimeters per annum, as there are in many of the arid regions of Africa, where the hydrogeological defining conditions are as follows. They can be taken as indicating a possible threat of quantitative overuse of groundwater resources. That is very low annual precipitation, high evaporation rate, large impermeable or shallow aquifer system, a restricted number of aquifers. The above factors are outside human control, but there are also other use-related factors which may lead to overtaxing of groundwater resources. Excessive close grouping of wells or pumps, right, due to poor coordination or ignorance, causes the cones of depression from the wells and pumps to overlap and thus cause an adverse effect on their yield. Uncontrolled rises in the abstraction rates due, for example, to enlarged livestock holdings and or greater use of water for irrigation or agriculture land. Wasting of water due, for example, to excessive running of pumps or modes of operation dictated by overlarge fitting pumps or ones with needlessly high output. Right. So these are some areas where human beings can play a role. In the above ones like low precipitation, high evaporation, impermeable system. Impermeable system means water does not go into the system, or you have small aquifers, right, which does not hold such a lot of water, and that also very few in numbers. Then it's a natural problem. We cannot do anything about it. As essential prerequisite for preventing overuse is an accurate as possible knowledge of parameters governing the hydrogeological balance or geohydrological balance, that is the inflow and outflow from the watershed in which the use is taking place. Often the basic data may not be available, and it may only be after observation over a number of years that adequate information on the parameters in question can be obtained, a fact that often mitigates against an early implementation of projects. Hence, overuse may equally well be the result of over hasty planning based on the observations made over too short a period. So you need to observe things over a large period of time, then only you can plan properly. In countries in temperate latitudes, preserving groundwater resources has traditionally been the primary concern of water management master plans. In arid regions, the need to preserve human life may sometimes mean that this primary concern has to be ignored and even groundwater has to be abstracted. However, any sustained overtaxing of such resources must inevitably lead to exhaustion of the resources and may thus, under certain circumstances, have high adverse long-term repercussion on the conditions of the life themselves. Problems of a purely mechanical kind, though ones which have major implications for supply, often occur with hand pumping, for which a wide variety of different systems are employed. Often the pumps break down for lack of only minor spare parts. These parts can then prove to be unavailable or there is no money to procure them, or no one will accept responsibility for getting them. As a result, the well can no longer be used and the population are forced to return to using surface water of unacceptable quality. It will be clear from the above that the questions of defined responsibilities of the techniques employed and of what the subsequent water charges need to be in order to ensure uninterrupted operation and proper maintenance are the very ones that have to be covered in a project and to be covered jointly with the target group with full involvement. Above all, the women who are responsible for fetching the water, right? So basically they need to look at who will take responsibility, what are the techniques that can be employed, what will be the water charges for providing continuous water supply and proper maintenance. These are some questions that need to be addressed in a project, right? And above all, you need to focus or give more importance to the transportation of the water, since women have to carry the water from one place to another place. So you need to find some means to do that also. Surface water, earthen dams of modest height, a few meters, are often built across or around rivers or river bodies, uh, or at the foot of suitable valleys or gorges in the associated watershed to store surface water for various purposes and make it available for long periods or all the year around. There will be only any impacts on the water balance and particularly on the groundwater conditions downstream of a small impounding work if the volume of impounded water amounts to be relatively high proportion of the discharge from the river or body of water when not intercepted, meaning impounding meaning storing of the water, right? Although this is seldom done, should the entire discharge be impounded, then the water course will dry up and the water table will be lowered. So you cannot store all the water there, right? Some water has to be released during periodic intervals so that the rivers don't dry up and the water table does not go down. It is advisable for a study to be carried out in each individual case and an estimate to be made on the basis of their findings of whether the volume of water abstracted will affect the ecology and if so how. At the same time, as accurate as possible, an appraisal must be made of whether total impoundment is justifiable in the light of the serious impacts on the water balance downstream. In the infiltration of surface water to replenish already overused groundwater sources with the added aim of cleaning the water as it seeps through the soil can only be contemplated when the general hydrogeological conditions are suitable and when adequate reserves of surface water are available, and it will therefore always be an exception. It makes better sense in case like this for the water to be filtered above the ground or for a water harvesting system to be installed along the course of the river in the form of an impermeable impoundment wall for collecting water facilities for withdrawal downstream and a filter structure facing upstream. Coming to the qualitative aspects of overuse and storage, so there are environmental impacts that can be caused by incorrect storage of rainwater and impounded surface water, and by contamination and illicit use of water as it is being conveyed in open channels. It is particularly in rural regions that the resulting hygiene risks of the transmission of waterborne diseases are high, in that in them surface water is generally freely accessible to man and the beasts. The water concerned is not subject to any sort of quota fixing and health risks are in general not properly appreciated. Deterioration of water quality is caused chiefly by suffocation with light and algal plant growth and by pronounced warming of the general static water. If there is also a rich supply of nutrients combined with a low rate of exchange of water, the eutrophication process may occur in the impounded water bodies, which are generally shallow. So the major problem with storage of water is that you will have some algae growth that is occurring, especially in surface water bodies. And even when you store water in homes, care has to be taken that some worms or germs, insects don't appear in them. So long-term storage is always a problem. Why? Because the quality of water will degrade. The health risks such as malaria, bilharzia, diarrhea diseases posed by stored water of this kind are compounded by the proliferation of insects, by the possibility of human and animal excrement on the banks and shores, and by discharge of wastewater. Another possibility is pollution resulting from the use of pesticides in the watershed where the water is collected. In this connection, care must be taken to ensure that strict demarcation of the watershed and physical separation of the water systems for human beings from those of the livestock. Where rainwater stored in systems, health risks arise as a result of deterioration of the water quality, which may be caused by long residence of the water in the systems and in some cases by choice of an unsuitable location, by lack of regular cleaning, by material related effects, or by direct entry of dirt and animals, right? Allowed by absence of covers or covers that do not seal tightly. Even chlorination of water, though it may be employed to kill off the bacteria, entails considerable health risks if not correctly applied. Right, overuse resulting from a good water supply system. A good water supply in rural areas can lead to an increase in livestock holdings with all the adverse consequential impacts this may have, such as overgrazing and blowing of the vegetation and compaction of the soil. In the longer term, there may also be tertiary impacts such as changes in the microclimate caused by attacks on the vegetation or water or wind erosion, where all the important topsoil is stripped away as a result of overgrazing of the vegetative cover. Detrimental impacts may also arise from the physical layout and position of the supply points when the latter are not geared to the socio-economic needs of the target group. Groups from a nomadic population, for example, need supply points that lie within a few days march even when the weather is bad and when the fodder is short. This may not be possible in certain instances, so the average length of stay at a gentle watering place is extended accordingly and the risk of overuse becomes greater. In the worst case, the nomadic way of life might have to be abandoned in favor of a quasi-sedentary way of life, and this would give rise to impacts whose social and socio-economic consequences would be difficult to foresee. In such cases, project schemes must be drawn up jointly with the target groups and must allow for existing, often traditional water and grazing rights, though at the same time by making provision for enlightening people and making them aware of the interrelationship that exists. They must also afford resource saving solutions. Interaction with other sectors, like how water sector is related with other so many other sectors, where a rural water supply has its closest point of contact is with all sectors that create further demand for water, that have the use of water as one of the direct or indirect objectives, or that affect water quality or restrict the quantity of water available. The chief sector concerned here is the agricultural sector, right? Why? Because water is generally used for agriculture purposes, right? Um, there may be a possibility of interaction too with the following subsectors, and such interaction should be checked for its consequences in individual case. So, plant protection, forestry, fisheries, aquaculture, irrigation, livestock farming, and agro industries, right? Water framework planning, rural hydraulic engineering, solid waste disposal, that is collection, treatment, and disposal, wastewater disposal, same collection, treatment, and discharge, river and canal engineering, erosion control, large scale hydraulic engineering, spatial and regional planning. So these are some areas where this rural water sector has some intersection or interaction with. Water supply occupies a key position in determining how and how intensively an area or region can be developed, and it therefore has an impact on all projects and sectors that involve planning to preserve, improve, or develop the infrastructure. Right? Thank you.
Thus, we come to the end of this session. Thank you for your participation. Looking forward to meeting you in the next session.